Hello everyone, my name is Kim, and both Youngin and I are here to present our image retrieval model, which utilizes the combination of global and local features. So here are the contents, the introduction, our method, architecture, and results. So this computer vision project aims to develop an image retrieval model which applies global and local features of the image. The model consists of the following: a backbone network, local and global descriptors, fusion methods, and an auxiliary module. A descriptor in the project is like a group of features combined into one vector. Having multiple descriptors has a similar effect of implementing an ensemble model with fewer parameters and lower complexity. The architecture of the model is illustrated on this page. From the backbone network, the local branch receives the feature map from layer 2, and the global branch receives the feature map from layer 3. Then the feature maps are then transformed into descriptors. Those descriptors are then processed into the orthogonal fusion model and a fully connected layer. Finally, all the outputs are then concatenated and fed into an L2 normalization layer. The final output is used to compute the metric loss. One of the global descriptors is processed in the auxiliary model to compute the classification loss. The classification loss helps the backbone model to produce a better representation. The local branch and the orthogonal fusion model was first implemented by Yang in the model.g. The local branch consists of a multi-address layer and a self-attention layer. The OFM combines the local and global descriptors as a projection and then is processed through the fully connected layer. To increase the performance, we integrated the following methods into our model: concatenating the descriptors, feeding feature maps from the second and third layers, and implementing an auxiliary module. There are mainly two ways to concatenate the descriptors. The first method is to concatenate the global descriptors and then feed the results into the orthogonal fusion model. The other method is to process the descriptors using the module to combine local and global descriptors together and then concatenate the final descriptors. As a result, the second method achieves a higher performance in all recall values. To generate local and global descriptors, feature maps from layer 2 and 3 are fed into the branches. We discovered that instead of using layer 3 and 4, it was better to use layers 2 and 3 instead. We assumed it was because of the resolutions of the feature maps. Layer 4 has a lower resolution than layer 3, which could have made it more difficult for the model to extract accurate features. We also implemented an auxiliary module that uses the cross-entropy loss, temperature scaling, and label smoothing. Our loss function consists of the following: the metric loss, the auxiliary loss, and the hyperparameter lambda. The total loss equals to the sum of the metric loss and lambda times auxiliary loss. Lambda adjusts the weight or the significance of the auxiliary loss has on the total loss. Two graphs on the left delineates the metric loss and the classification loss. The graphs on the right are the accuracy plots. The green, blue, and red trends on the graph represent the following: the models that trained with an auxiliary module throughout the whole training session, or for only two epochs, and no auxiliary module respectively. You can see that on the classification loss graph that the red trend is 0 and the blue trend reaches 0 after the second step because the auxiliary module, which uses the cross entropy loss, is not used. At the start of the training session, having an auxiliary loss further enhanced the accuracy, but the accuracy decreased as the session went by. We assume it is because classification is relatively easier than metric learning for a model to learn and therefore resulted in the classification loss to converge quickly. If you look at the C-loss graph, you can see that the classification loss converges after the fifth epoch. Therefore, we utilize the auxiliary model for the first two epochs only. To exploit the faster convergence rate, we try to utilize the model only for the first two epochs. It was better to include the model in recalls at 1, 2, and 8 when lambda equals 3. The table on the left is a set of results we obtained when lambda equals 1. When lambda equals 1, there's not much significant amelioration to include an auxiliary model. The tables manifest that we were able to achieve the best performance when lambda was 3. This table manifests the performance of the model depending on what kind of global descriptors were used. At the top of the table, we included the performances of CGD, a model which did not implement a local descriptor. As you can see, our model that employed both local and global descriptors had a better performance. As a result, the highest performing module will consist of MAC and GEM functions on the global branch with an auxiliary module with a parameter lambda equals to 3. We empirically found out that the lambda of 3 achieves the best performance on the day of the presentation, which was after we submitted our paper. We did not know this when we were writing our paper, but wanted to share the final results. Please be noted that the results on our paper and those on the presentation are different. Ultimately, we developed a model which uses global and local descriptors to take advantage of both local and global features. Feature maps with a suitable resolution and an auxiliary module which affects the final loss. Thank you for listening, and if you have any questions, feel free to contact us by email or read our papers for more details.